Okay, so welcome back. So it starts off very easy, very straightforward, okay? So obviously we labeled the diagrams, solid, liquid, gas. I think that's pretty straightforward. And then which physical state, if they're all at room temperature, which one has the strongest attractive force? And which has the weakest? Gas, okay? Now that's if it's different substances at the same temperature, room temperature, whatever. So attractive forces don't change strength. You know, even though you start heating something up and go from a solid to a liquid to a gas, the attractive force doesn't change. The amount of energy the molecules have changes, and so they can overcome those attractive forces, and the attractive forces become less significant the hotter it is, the faster they're moving, and all that. All right, so we can do that. Now this is just something that I want you just always just pay attention to. First off, these are very general. Every ionic compound, every ionic bond is going to have a different strength. And when we get into thermo, we'll look at bond strengths and those things. This just gives us ballpark. Okay? This is an approximate average, you know, for an ionic bond versus a covalent bond. There are some covalent bonds that are stronger than an ionic bond, but in essence, covalent and ionic bonds are strong. Compared to, when you go to the next page, and this is the one I didn't have on there, which, you know, is the most important one. How do these intermolecular forces compare with the ionic and covalent bonds, which would be intramolecular forces? How do these compare in strength?
These are weaker.
Are they just kind of weaker? Like way weaker. The strongest hydrogen bonds is only 1/10 just what a normal covalent bond is going to be. So these are by far the weakest link. So the hydrogen bond is the strongest of your IMFs, but IMFs as a whole are much, much, much weaker than your covalent bond, ionic bond, metallic bond, any of those. Okay? So these are the ones that are going to break first. So when you boil something, you're not going to break the covalent bond holding the hydrogen to the oxygen. You're going to break the water molecule from water molecule from water molecule. So again, what's in the bubble when water's boiling? Water vapor. It's not air. It's not hydrogen and oxygen. It's water molecules breaking apart from one another. Okay? So obviously, list group A and the types of interaction in order of increasing strength. You can put those 800, 400, 40, 25. I mean, that's easy. Okay? Now, so when you're boiling water, what bonds do you think you're breaking? The intermolecular ones. Okay? You're not breaking the covalent bonds. That is a question that they'll ask. Okay? So if I'm looking at something like CO2 solid going to CO2 gas. First off, what's that process of solid to a gas called? Sublimation. Okay? But what type of bonds am I breaking here? IMFs. Okay? And specifically CO2, we're going to learn and we're going to memorize everything there is to know about CO2. We're going to know that this is one of the most common non-polar molecules because it's a symmetrical shape, but it's non-polar. So the same thing here. So this is in a AP question, and these were two choices. You know, as far as you know, which one is are covalent bonds broken? Is a covalent bond being broken here? No. What bond's being broken? And since it's I2, is this going to be polar or non-polar? So what IMF is going to break? LDFs. It's only going to have LDFs. Okay? But if I said something like a diamond going to carbon gas, okay? So now if I take a covalent network substance and I break this diamond into a gas, what bond do I have to break? How is carbon bonded to carbon bonded to carbon here? Covalent bond. So what type of bonds are we going to have to break? A covalent bond. Okay? So in a covalent network substance, you're gonna have to know that it's covalently bonded. If you break those, you're gonna be breaking a covalent bond. What if I said NaCl solid going to NaCl liquid? So what? I'm gonna break an ionic bond. I'm gonna have to overcome the Coulombic attractions of Coulombic force, but I'm breaking an ionic bond here because to melt an ionic compound, you gotta break the Na plus from the Cl minus. You're actually breaking the ionic bond. Ionic compounds don't have IMFs because they don't form molecules. Okay? Ionic compounds don't have IMFs because they do not form molecules. They form big crystals. So we don't have IMFs in ionic compounds. Ionic compounds only apply to covalent molecular substances. They're intermolecular forces. So they're only going to apply to molecules. Only covalent molecular form molecules. Okay? That's important. All right. So obviously, which are stronger, group A or group B? Okay? We know all that. Okay. So now it says to apply, let's spend some time here on this one. Okay? Let's spend some time on this. First off, how can we tell if it's polar or non-polar? Electronegativity, but we don't have electronegativity. On the AP test, you don't have electronegativity charts or values. Phone call. Okay, here's another rule. If it's just a hydrocarbon, hydrocarbons are always nonpolar. So if it's just carbon and hydrogen, doesn't matter how many there are, how big it is, the shape of it is, if it's just carbon and hydrogen, it's going to be nonpolar. Basically a symmetrical molecule, it's going to be nonpolar always. So why does C2H6 have a higher boiling point than CH4? Okay? Is it molar mass? Well, first off, if they're nonpolar, what's the only type of IMF? LDS, London dispersion forces. And with what do London dispersion forces, what does the strength depend upon? Now this whole packet said it's based upon what? No. The boiling point is the measure of that, but what does this packet say? What is the relationship?
Size of electron?
Well, that's the right answer, but what does this packet say it's based upon? The molar mass. Okay? But we're going to change anywhere the packet says molar mass, we're going to change the size of the electron cloud. Okay? So why then does C2H6 have a higher boiling point than CH4? It's got a bigger electron cloud. So here's our answer. So if I'm going to give you a free response question, given this, explain why in terms of the types and strengths of intermolecular forces present, why does C2H6 have a higher boiling point than CH4? C2H6 has a higher boiling point, although well, I'd say both C2H6 and CH4 are nonpolar molecules that only contain London dispersion forces between the molecules. And we're always going to stress these are IMFs, they're between the molecules. Okay? However, C2H6 has a larger electron cloud than CH4, causing it to be more polarizable. That's a favorite AP word. More polarizable. That's that induced dipole. It's polarizable. The electron cloud is more smushable. Fancy word is more polarizable than smushable. Okay? It can distort more. It's more polarizable, meaning it's going to have electrons more on one side than the other side. It's more polarizable, causing it to have stronger London dispersion forces, which require more energy to break the molecules apart from each other. Thus, it has a higher boiling point. That's your answer to the free response question. Okay? C2H6 has a larger electron cloud, makes it more polarizable, causes it to have stronger London dispersion forces, requires more energy then to break the molecules apart from one another, so it has a higher boiling point. Again?
You know it has more electron clouds than one.
Now, the practical is we look at the molar mass. The bigger molar mass is going to have a bigger electron cloud. We just can't say it's got a bigger molar mass. We're just going to say it's got a bigger electron cloud. Okay? But the practical is we look at, well, it's just bigger, so it's got a bigger electron cloud.
So like ions, right? You could have like a less mass and it'd be a bigger electron cloud, and that would.
They're very rare. I don't know if I know of a case where it's got a smaller molar mass and a bigger electron cloud. But you can't, but it's all based upon the electron cloud being distorted, so AP wants you to talk about the electron cloud, not how heavy it is. It's not based upon how heavy it is, it's based on how polarizable is that electron cloud. Okay? So we're always going to say electron cloud. Alright, so that's just comparing these two. Okay? So I'm kind of adding into this here a little bit. So now, all of a sudden now we go to HCl, okay? And it's negative 80, okay? These are close to one another, but what type of molecule is HCl in terms of polarity? Polar, how do I know? Phone call. Okay, so this is polar. So these are LDFs only. Okay, and so we can explain the difference here. This, what type of, if it says list all the types of IMFs present, what are we going to say for HCl? LDFs, always LDFs, and dipole-dipole. Okay? Now, 24, this is 30, okay, so this is going to be 35.5 plus, so 36. So this one, so this is, what did I say, 24, this is 30 grams per mole. This is 36.5 grams per mole. So a little bit bigger electron cloud, okay? But what does this also have? Dipole-dipole. Okay, because HCl, you know, they have very similar London dispersion forces, but because HCl is polar, it also has the stronger dipole-dipole attractions. Thus, it takes more energy to break the molecules apart from one another. It's going to have a higher boiling point. But then we go to these two. Okay, why is there, HF is pretty small, smaller than HCl. So the electron cloud of F is smaller than chlorine. So why is this boiling point higher? Because now it can hydrogen bond. They always look for the hydrogen bonds. Okay, so both of these are going to have what, if I was to list the types of IMFs, what are they going to have? Times fine. LDFs, dipole-dipole, and H bonds. Okay? So even though HF has a smaller electron cloud than HCl, and its London dispersion forces would be weaker, because it also has dipole-dipole and hydrogen bonds, that HCl does not have hydrogen bonds, it's going to have a higher boiling point than the HCl. But why water then? This is 20 grams per mole, this is 18. That's relatively close. LDFs are about the same. Not much difference there. The electron cloud is about the same size. But HF is going to look like this, to where then another HF can come in and bond here. This is my H bond. Why do you think water is even so much higher? I just heard a mumble. 2 H's. So when water bonds, you've got 2 H's, so a water can come in here and form a hydrogen bond, and a water can come in here and form a hydrogen bond. And really another water could come in here and form a hydrogen bond kind of like that. Okay, so it's got multiple spots, multiple ways for the hydrogen bonds to form, so the water molecule is going to be stuck together much more tightly. As a result, it's going to have a higher boiling point. Now here's the thing. The boiling point is always the indicator of the strength of attractive forces. I heard somebody saying that. The higher the boiling point always means stronger attractive forces. So if you have a big nonpolar molecule it could have a stronger attractive force than a small polar molecule. Okay? So it's a boiling point always wins. Boiling point's the ultimate determiner. So you have to base your answer based upon the data that is given. Okay? Now, I know that the bell's about to ring, but we're supposed to get all the way through this worksheet. Stay with me. Okay? So, look, we assigned each. So the more polar the molecule, what does that mean about the boiling point? The higher. The more polar the molecule, the stronger. So when I look now here, if they're all diatomic like this, what do we know about the polarity? How do we know that? What's the difference in electronegativity going to be between the two? 0. These are perfectly nonpolar. So what's the only type of IMF? LDFs. So what do LDFs vary with? No. Size of the electron cloud. So as we're going down, the electron cloud's getting bigger. So the LDFs are getting stronger. So it takes more energy, higher temperature to break the molecules apart from one another. So based upon your answer, okay, so this is gas. We looked on the periodic table: gas, liquid, solid. Okay? Based on your answers, which must have the strongest IMFs? Obviously iodine, because it's got the biggest electron cloud, strongest London forces. Okay? Is there a relationship between polarity and boiling point? No. What's the relationship between size of the electron cloud and the boiling point? What's the relationship? The bigger the electron cloud, the more polarizable it is, the higher the boiling point. All right, we'll pick that up tomorrow. Go Jags. Just stop that.